Alright, so now let's start getting into some of the actual specific details of how we're going to write up a code that will solve this. So, let's see here. So, let's see, I remember I took a class on finite element methods, and in this class, this is sort of the type of. We had a couple of projects where we implemented finite element methods, and this is a this is the polynomial basis that we used. Is just polynomials of this form, and you can go ahead and graph these if you want. I believe what they look like is zero. So if you've got your if this is your interval I1 and this is your y-axis, and of course this is going to be 0, then you've got your constant function looks like this, your linear function looks like this. Then I'm pretty sure well, let's see here. Then from here we can actually just figure out what everything else is going to be, because it's just going to be this linear function squared for the quadratic, and so that would look like this or something like that, etc. So this is, of course, this is going to be 1. It's going to be minus 1. All right, and so is that right? For L equals 1, maybe it's 1/2. Well, let's actually look at this. Oh, well, yeah, it is 1/2, because look at the next line here. So, phi 1 at the right endpoint, which is xj plus 1, is going to be 2 to the minus 1, so it's going to be 1/2. So this is, if this is 1, then the linear function is going to look like this. Quadratic is going to look like this or something. It's going to be pretty narrow. But in any case, you can solve for what phi L is going to be at each endpoint. And so on the right endpoint, it's always going to be positive. On the left endpoint, it might be negative depending on the degree that you're using. And then, so yeah, using that, this is just evaluating phi L j. But what if you have phi L j plus 1 or phi L j minus 1? And what if you're evaluating these from the left and from the right? Then sometimes, so if you're evaluating phi L j at the left, so if you just, here, let's draw again ij. This is going to be xj minus 1/2. It looks like throughout this write-up, I was using j plus 1/2 and j minus 1/2 instead of xj plus 1/2 and xj minus 1/2. But, I mean, I don't know, sorry, I guess, but also this write-up is more, this is more like personal notes so that I know how to do this, so as long as I understand what I'm doing, I'm good. But hopefully, me in the future will understand what I am doing now, but that remains to be seen. Anyways, so this is ij, woof. This is ij, then phi Lj minus at j plus 1/2 at xj plus 1/2. So you're approaching the right endpoint from the left, and so you're going to evaluate that within ij. Similarly, phi Lj plus at j minus 1/2. So you're going to approach the left endpoint from the right, and so you're going to be evaluating this within ij. However, for phi Lj minus 1 minus, so you're at the left endpoint, and you're evaluating it from this way. And so you have to move to ij minus 1 to see what's happening. However, these basis functions are translation invariant because you've got the same basis on each cell. And so evaluating phi Lj minus 1 from the left at xj minus 1, so you're just taking phi L, you're taking this particular phi L and evaluating it at the right endpoint. So that's going to be exactly the same as if you were to take phi Lj and evaluate it from the left at xj plus 1/2. So that's going to give you 2 to the minus L, as we saw in the first equation. And similarly, if you approach phi Lj plus 1 from the right at its left endpoint, then you have what we had in the second equation. Okay, and so now using all of this information, we can rewrite that system of equation that we had from before. So I've gone ahead and pulled the sum of the ULM plus 1j's out so that you have this integral here as a coefficient. And then here I've gone through and replaced a lot of those. So there's some phi terms there's some terms where you're taking integrals of phis, and those need to stay because we don't know what those are yet. But then for some of the terms, we were evaluating these basis functions at particular endpoints. And so I've gone ahead and replaced them with these. And so you might want to go back and just make sure that you see how all of this works. But yeah, this is just algebraic manipulations. Okay, so now we're really close to our actual linear equations. And for each particular ij, we can actually write it out. So, for example, if we look at the sum from 0 to k of ul n plus 1j of the integral over ij of phi lj phi mj dx. So, for each particular m, we want this to hold for m equals 0 through k. And so each of those gives us an equation. And so we've got m equations here. No, we've got k equations. No, we've got k plus 1 equations because we're going from m equals 0 to k. So we get k plus 1 equations. So we transform that into this, where m is a k plus 1 by k plus 1 matrix, and it's given by this. So instead of this being like mij, typically like you write a equals aij, where aij is the entry in the ith row in the jth column. However, I'm already using I and j here, so I don't want to use that again because that'll be confusing. So instead I use m and l because I'm not using those, or because I'm using those, but they correspond to, m corresponds to the row and l corresponds to the column. And so row m and column l will be this integral of phi l minus 1j times phi l m minus 1j. Now, I'm subtracting 1 because when I put this into MATLAB, this is coding. So we have to worry about off by 1 errors because those happen all the time, and you have to be careful about those. So what's happening here is in MATLAB you number the rows and columns from 1 to however many rows you have. You've got. So in this function, or for this problem, we have m equals 0 to k. So we've got k plus 1 different m values. And so m ranges from 0 to k, but there are k plus 1 values. So the matrix needs to correspond to the index of the m value, not the m value itself. So the first row of the matrix M corresponds to the first row of this matrix corresponds to lowercase m equals 0. The second row of this matrix corresponds to lowercase m equals 1, etc. And so that's why I have these L minus 1s and M minus 1s here. Okay. So we can sort of see how we get there, because if you fix an M, then you take the sum from 0 to k of this thing. Well, that can be written in vector form. So you can take u0 and j through uk and j. and you're multiplying that by, so let's see here, for m equals 0, you have the integral for ij of phi 0j dx all the way up to the integral over ij of phi. I'll just include the phi mj dx here. And then we're going to go all the way up to phi kj phi mj dx. But I'm not going to write the dx because of the space. So we have a row vector here and a column vector here. And when you multiply these two together, what you get is this sum here. Or yeah, you get this sum here. And if you combine this for every single m from m equals 0 to k, you get this matrix I've written here. M times un plus 1j. Un plus 1j, of course, is the matrix consisting of here. So this should be un plus 1j 0, then un plus 1jk. Okay, so that's how we get that. And then you can sort of trace through and see how we convert all of these other things into matrices. But of course, we have to write out what the matrices are. So some of these matrices depend on both rows and columns. Most of them do. Some of them only depend on the row. Some of them only depend on the columns. And again, you have to worry about, whereas up here you see things like minus 1 to the m times 2 to the minus l minus m. So that's over here. And so, let's see here. So that's why instead of minus 1 to the m, you get minus 1 to the m plus 1. Because you have to subtract 1. And instead of 2 to the minus l minus m, you get 2 to the 2 minus l minus m, because you have minus l minus 1 minus m minus 1. So you end up with minus l minus m minus negative 1 minus negative 1, and so that's just plus 2, so you have 2 minus l minus m. Okay, and you can check through that these all work, but we have this matrix equation for each particular ij. Now we still have this j minus 1 here and this j plus 1. Oh, and by the way, you see these dot products here? That's element-wise. So if you see, like up here, so we've got this minus dt, then we've got qln j minus 1. We've got minus 1 to the m times 2 to the minus l minus m. That's why we multiply by b and c here. Because, let's see here, b takes care of the 2 to the exponent, and then c takes care of the minus 1 term. And so you're multiplying these matrices element-wise rather than taking actual matrix product. So that would be like 1, 1, 2, 3 times 2, 1, 2, 1 equals, so 2 times 1, 1, 4, 3. So that's what this dot product is that we see up here. Okay. So now we have these two matrix equations for every single j, or for every single j, but we want to solve these for all un plus 1j's we want to solve for these for all vectors simultaneously, because like you can see here, for example, just look at the second equation. So you've got an equation involving qnj, which depends on unj and unj plus 1. And so then the equation for qnj plus 1 will depend on unj plus 1 and unj plus 2. And because we're using, I guess I haven't mentioned this, because we're using periodic boundary conditions, when you get to the right endpoint, it loops around. So anyways, if we want to combine these all together, this is what we get. So we see the only place that so basically each of these capital M's is just a block matrix. It's exactly the block that we saw above. So let's remember this: M, 2M, minus delta t, and a bunch of stuff. Okay, so now if we look at this first block here, we've got m, we've got a 2 times m, we've got a minus m, and then we've got minus delta t times a bunch of stuff. Now, let's look at this. We've got a minus b, which corresponds with q and 0, and a b times c, which corresponds with q and k. And that makes sense because that was for the first cell. And so the a minus b would correspond with j equals 0. And then for the b times c term, that corresponds with the j minus 1. And so you go with the previous cell. But if you go j minus 1, then you loop back around to the very end. And so you're back at... I don't know if that's supposed to be k. I think that's supposed to be, let's see here, it should be n, because n is the number of... It should be the total number of... It should be this should not be k. It should be the total number of intervals. The total number of spatial intervals. So let's see if did I give a range for j at all? Let's see here. What things are we not using? K, L, M, N, O, P, Q, R. So your finite element, or space, S. Let's use S. So this should go from 1 to S. So if we look up here, so this equation, this should hold for j between 1 and S. S is the number of spatial points. Of course, I defined that in my code because if I didn't, it wouldn't work. So this should be from 0 to S. Wow, my computer is getting really hot. I've been doing a lot of filming, and it is like 80 degrees outside, so even though I have the AC blasting when I'm not filming, I can only do so much. So, the above matrices are capital N by capital N block matrices. So I do have a variable that I'm using, capital N. Capital N is the number of cells that we're using. So this should be j between 1 and capital N. Alright. So that's how we do this. And each block is a k plus 1 by k plus 1 matrix. As we saw, like all these m's here, for example, it ranges for m. The indices for the rows and columns are m and l, which are so those are going to range from 0 to k because the finite element space is pk. Okay, and so here we go. So now what we have is we have this vector. So this vector on the right here gives us un plus 1. It gives us all of the un plus 1 information, and it depends on the un information, the un minus 1 information, and the qn information. Here when I say n, I mean lowercase n. I know it's confusing. Sorry. For the bottom equation, we have qn, and it depends on un. Now, of course, you might be wondering, this matrix of capital M's, this block matrix, is it invertible? It turns out it is. It turns out you can prove that. I'm not going to worry about that. Yeah. So this works. And you can see, like, okay, so if you know all the information for up to lowercase n, then you can use the top equation to get all the un plus 1 information, and then you can use that to get the qn plus 1 information in the bottom equation. Okay, so that's the inductive process. And now we need to worry about the initial conditions. Okay, so first, UH0, the initial condition at the very first time point, is just going to be this projection. And this is a particular projection that's discussed in the textbook, where you project it in such a way that typically when you would project it, so you see this equation here, this integral of whatever equals this integral. So integral of the UH0 times phi m equals the integral of the exact times phi m. And this should hold for every single phi m in the, or this should hold for every single, you can replace phi m with v, and this should hold for every v in the polynomial space. However, because it's a polynomial space of finite dimension, you can just make it hold for every phi m, where phi m takes on the basis functions. However, we're doing pH plus, which is a different projection. So instead of making this hold for all polynomials of degree up to k, you only force it to hold for polynomials up to degree k plus 1, and then you have this extra degree of freedom, and you use that to ensure that this function takes on the correct value at the right endpoint? No, this is xj minus 1, so it's at the left endpoint. So you make sure that the initial condition is exactly correct on the left endpoint. And so this gives us a system of equations. So that first equation with the things I have underlined or bracketed, that holds for m between 0 and k plus 1. So that gives us the first k rows of this matrix. And you can see that you can just write it out like this. And then the final thing, in order to make sure that each that you get the exact value at the very end point, you use that last row. And so all you have to do is just put these matrices in the MATLAB and solve for the U0 coefficients. And the nice thing that I mentioned is that this matrix equation, this holds for a particular ij, but there's no information that you need to take from other cells, so you can solve for each individual cell separately. And that's really nice, that's really convenient, because then you don't have to set up like a weird matrix like the ones that I showed earlier where you're taking things from neighboring cells. Oh, I guess another thing that we can mention about this, just while it's on my mind. So notice that, so this a minus b and this b times c, the b times c always comes from the cell to the left, because that's the way that information flows for the q's. Whereas for the second equation, we see the b times e terms. By the way, this is a break here between these. We've got one entry here and another entry here. They're separate entries. So yeah. This is a typo. This should be b times e. And this should be the minus a minus b times d. But yeah, we see for this one that the b times e term comes from the cell on the right. And that's because for the u's, the info flows from the right. And that's sort of what we talked about with the flux terms. Anyways, moving back here, we've got the UH1 to deal with. And this ended up being very difficult to deal with, because here's what we do. We take, so this is the UH1, and this is the UH0, and then you've got to add this other stuff here. Remember, like I said, the ends for n odd, you have a factor of PHV0, and that drops out because PHV0 is 0. Because the initial condition for this particular problem is the time derivative is 0. So we only have the even terms that we worry about. Alright, so here's the issue. When we compute this, we're taking derivatives of our basis elements. And when you take a derivative of a basis element, that doesn't necessarily give you a basis element. So once you take the derivatives here and you figure out this polynomial, the polynomial can only be written at first, when you first compute it, it's written in terms of the standard basis, being 1, x, x squared, x cubed, etc. That standard basis of the space of polynomials. However, it's not written in the finite element basis. So you need to do some stuff to convert it to the finite element basis. And this is typical, was it like Gram-Schmidt, I think? Just a standard procedure for switching the basis. This might not even be Gram-Schmidt. This might just be algebra. But yeah, so we've got this formula here that allows you to figure it out, how to do it, and it ends up being a little complicated and tricky to do. But yeah, so once we do this, we figured out how to get UH0 and UH1, because UH0 we get from projecting the initial condition, and UH1 we get from UH0 using this projection here. Now, QH0 we don't actually really need, but now let's move on to UH2. Now for UH2 we need UH1, UH0, and QH1. Now the way we get QH1 is we get it directly from UH1. Because you just take UH1, remember Q is just UX, so Q is the spatial derivative of U. So for QH1, we just take the spatial derivative of UH1 and we're good to go. And of course, if you want to get QH0, you can just take it from UH0, but it's not useful. Anyway, so for UH2, you need UH0, UH1, and QH1. And then once you have UH2, you can get QH2. And then you can continue this, because UH3, you need UH2, UH1, and QH2, and then QH3, you just get it from UH3. And that's your process. From this point on, you're good to go. And that's how you find all of the UHs and all of the QHs for all of the discrete time points. And so now you've got a running code. So the last thing that we have to do here is actually implement it in MATLAB. And that's what we're going to talk about in the next video.